Hello everyone, I am Dr. VRAO. Today I am here with a new chapter, that is electrochemistry. Electrochemistry. Why electrochemistry? Because in the earlier classes we had gone through the ionic and chemical equilibrium chapters, and those chapters will help you in understanding electrochemistry. That is why I start this electrochemistry chapter, right? So before we are going to start electrochemistry, what is the significance of electrochemistry? The subject electrochemistry has been increasing the quality of human life. For example, today we are all using inverter technology, inverter batteries. Those inverter batteries can supply electrical energy even in the absence of current. So we are happily enjoying our life in the absence of current also. In that inverter batteries, chemical energy is converted into electrical energy. That is why that chemical energy is providing electric energy, and by that electric energy we are happily leading our life in the absence of current also. And nowadays we are using bike batteries, car batteries, remote batteries, watch batteries, everything, what not. So in this way electrochemistry has been increasing the quality of human life. Photoelectric cells, all these are the applications of electrochemistry. Now what is electrochemistry and what with it deals? Electrochemistry deals with the conversion of electric energy to chemical energy, and it deals with the conversion of chemical energy to electrical energy, right? Electrochemistry deals with the conversion of electrical energy into chemical energy. And electrochemistry deals with the conversion of chemical energy into electrical energy. So the subject electrochemistry deals with the conversion of electrical energy into chemical energy and conversion of chemical energy into electrical energy. And moreover, electrochemistry deals with the study and preparation of chemical substances. So we know what is meant by electrochemistry. Electrochemistry is a branch of chemistry that deals with the conversion of electric energy into chemical energy and conversion of chemical energy into electrical energy, and it deals with the study and preparation of chemical substances, right? So we all know that conversion of electric energy into chemical energy, which can be done by electrolytic cell, and conversion of chemical energy into electrical energy, which can be done by voltaic or galvanic cell, or more commonly we can convert the chemical energy into electric energy by Daniell cell. So, in nutshell, electrochemistry deals with the conversion of electric energy into chemical energy and conversion of chemical energy into electrical energy, right. So, before we are going to understanding the electrochemistry concepts, we should know the terminology of electrochemistry, which includes conductor, types of conductors, right, conductance, specific conductance, equivalent conductance, molar conductance, etc., etc. These are the terminology of electrochemistry. Now, let us see one by one, right. Let us go through the terminology of electrochemistry one by one, right. So, at first we shall see what is electric conductor. What is electric conductor? So, electric conductor. Electric conductor. The substance electric conductor is a substance which allows electrical current through it is called electrical current. For example, electrical current is regarded as a flow of electrons. Electrical current is regarded as a flow of electrons through a conducting medium. That conducting medium is called electric conductor. So, electric conductor is a substance which allows electrical current through it is called electric conductor. So, we can say that electric conductor is a conducting medium because electrical current is regarded as a flow of electrons through a conducting medium. That is called, that conducting medium is called electric conductor. And this electric conductor may be a solid, right, fused salts, fused metals, aqueous solutions of acids, bases and salts, right. So, electric conductor may be a solid or fused salt or fused metals or aqueous solutions of acids, bases and salts. All these can act as electric conductor, but in this case, a solid case, conductor is a solid, okay. But in this case, aqueous solution of acids or bases or salts, in this case conductors are liquid solutions. So, based on this fact, because conductor may be a solid or fused salt or aqueous salt solution or aqueous acid solution. So, based on this, conductors can be classified into two types. Conductors can be classified into two types. One is electronic conductors. One is electronic conductor and is electronic conductor. And the second one is electrolytic conductor. Right. So, conductors are classified into electronic conductors and electrolytic conductors. So, electronic conductors, examples for electronic conductors are metals. Examples for electronic conductors are metals, because in this electronic conductors, current is being carried by electrons. That's why we call it as electronic conductors. In metals, electrons are there. So current carriers are electrons. That's why we call it as electronic conductors, right? And electrolytic conductors. Electrolytic conductors, examples for electrolytic conductors are aqueous solutions of salts, acids, bases. These are the examples for electrolytic conductors, because in which current carriers are ions, whereas in case of electronic conductors, current carriers are electrons, right? So electrolytic conductors are examples are aqueous solutions of salts, acids, bases. For example, if you take salt solution, for example sodium chloride solution, Na plus ion and Cl minus ion. So current carriers are ions, right? That's why we call it as electrolytic conductors, right? And one more thing is that okay, electronic conductors and electrolytic conductors, both these conductors do follow the Ohm's law, right? Okay, let us see what is Ohm's law. Right, Ohm's law. Right, one thing that you should remember in your mind is that whether it is electronic conductor or electrolytic conductor, that do follow Ohm's law. Ohm's law is at a constant temperature, the electrical current I in a conductor is directly proportional to potential difference between its ends, right? I repeat, Ohm's law, at a constant temperature, the electrical current I in a conductor is directly proportional to the potential difference between the two ends. That is, potential electrical current in a conductor is being represented by I, right? And the potential difference between the two ends. For example, if you take electronic conductor, that is copper wire, okay, if you take a copper wire, okay, so if you take any conductor, if you take any electronic conductor, so that is that has that one at one end has its own potential, and there is another potential at another end. There is a difference between the potential difference. There is a difference between the potential of at the two ends, right? So potential difference, that potential difference is being represented by V. So the current passing in the conductor, that is I, electrical current passing in that conductor is directly proportional to potential difference between at two ends, right? So that is V is proportional to I, or I is proportional to V. So usually we write it as V is proportional to I, and if we remove the proportionality, and we can write as Ri, V equal to Ri. Usually we can write it as we write it as V equal to IR. Okay, in the earlier classes we learned this Ohm's law with a magic triangle, that is V equal to IR, right. So, V is directly proportional to I and R equal to V by I equal to V by R and V equal to IR. Okay, this is the magic triangle by which in the lower classes you all learnt Ohm's law, right. So, V equal to IR is the Ohm's law. This, what is this proportionality constant? R. R is called resistance. R is called resistance. What is resistance? We know that conductor, what is conductor? The substance which allow electrical current through it, okay, and we know the electric current and we know the potential difference, but what is R? R is resistance. R is resistance. R is called resistance. What is meant by resistance? Resistance is, it is a opposing force to the free flow of electrons. It is a opposing force to the free flow of electrons, right. I repeat, resistance is, it is a opposing force to the free flow of electrons. It always trying to oppose the free flow of electrons in a conductor. That opposing force is called resistance, and that resistance is directly and that resistance, that is the proportionality constant. So, resistance is defined as it is a opposing force to the free flow of electrons, free flow of electrons. So, R equal to V by I, R equal to V by I. So, usually V potential difference that is being measured in volts, okay, and electrical current I in amperes. So, volt per ampere, units for resistance is volt per ampere, and usually we can write it as a ohm. What is that? Ohm. So, resistance units are ohm, right. So, this is resistance. So, this resistance you have to know, you have to apply this concept to electronic conductors. Already we applied this Ohm's law to electronic conductors. That is why if you take a electric conductor and if electric current is I and V is the potential difference at the two ends, and the electric current I is directly proportional to V, okay, V equal to IR. So, we applied the Ohm's law to electronic conductors. But what I said, Ohm's law can be applied to electronic conductors as well as electrolytic conductors also, electrolytic conductors also. So, let us define this resistance, in electrolytic conductors, okay. So, before we are going to apply the Ohm's law to electrolytic conductors, we have to know the conductivity. We have to know what is meant by conductivity. Conductivity is movement of ions. Conductivity means movement of ions under the applied voltage is called electrical migration or mobility or ionic conductivity, right. So, what is meant by conductivity? Conductivity is the movement of ions under the applied voltage, that is called mobility or ionic conductivity or migration of ions, right. Now, we shall apply the resistance, definition of resistance to electrolytic conductors. But before, one more thing is that in electronic conductors, we can measure the resistance with Wheatstone bridge. We can measure the resistance in electronic conductors by Wheatstone bridge. Wheatstone bridge, right? Now we shall apply the concept of that is resistance definition to electrolytic conductors, right? Now, and in electrolytic conductors, what is resistance? It is the opposing force to the mobility of ions. It is the opposing force to the mobility of ions is called resistance, right? So you please keep this point in your mind. In electronic conductors, resistance is a opposing force to the free flow of electrons, whereas in electrolytic conductors, it is the opposing force to the mobility of ions, right? Mobility of ions, right? So in electronic conductors, resistance can be measured by Wheatstone bridge. In electrolytic conductors also, we can measure resistance with the conductivity cell. What are electrolytic conductors? Electrolytic conductors are aqueous solutions of salts, acids and bases. What are present in that aqueous solutions of salts, acids or bases? Ions are present in that aqueous solutions of salts or bases and acids, right? So the resistance is opposing force to the mobility of ions in electrolytic solution, right? So that resistance is being measured by conductivity cell, okay? That is conductivity cell, right? Okay. So conductivity cell, in conductivity cell, okay, conductivity cell by which we can measure the resistance, in electrolytic conductors. Conductivity cell is it is in the form, okay, it has two platinum plates, okay, separated by a unit distance, right? So conductivity cell consists of two platinum plates. This is one plate and this is another plate. Okay, these two plates are separated by a unit distance of 1 centimeter, okay, and its cross sectional area, and its cross sectional area is 1 unit cross sectional area. And in this conductivity cell, the two platinum plates are separated by a unit distance, right? There is a unit distance. So already I told you Ohm's law is applicable to electronic conductors and electrolytic conductors, right? In electrolytic conductors, the resistance of electrolytic conductors, that is when we dipped this conductivity cell in a aqueous solution of salt or acid or base, that measures the resistance, of course, and that resistance is later converted into conductance, and that means conductivity cell measures not only resistance, it measures conductance also, because reciprocal of resistance is called conductance. That is why conductivity cell not only measures resistance but also measures conductance, right? So if you dip this conductivity cell in aqueous solution of salt or acid or base, what happens? What happens? This conductivity cell measures resistance. Resistance. What is resistance? It is the opposing force to the free flow of ions or mobility of ions in case of electrolytic conductors. So, that resistance is directly proportional to length between the parallel plates. That resistance is directly proportional to length between parallel plates. This is the length and its cross sectional area is A. Okay. So, that resistance is directly proportional to L, that is resistance is directly proportional to length between the two parallel plates, and resistance is inversely proportional to cross sectional area of this cell, right. So, resistance is now we can write resistance is directly proportional to L by A. Resistance is directly proportional to L by A, and if we remove the proportionality, resistance is equal to some constant rho into L by A. L by A, where rho is called specific resistance. Specific resistance means 1 unit length and 1 centimeter square cross sectional area. Okay. So, specific resistance is resistance at 1 unit length and 1 centimeter square cross sectional area. So, rho is a specific resistance. So, rho is equal to R into A by L, R into A by L, where rho is called specific resistance. Rho is called specific resistance. Specific resistance. Nowadays, this specific resistance, the term specific resistance is specific resistance is replaced by the term resistivity. Resistivity. What is it called? Resistivity, replaced by a new term called resistivity. So, specific resistance or resistivity, these two are one and the same, right. So, rho is equal to specific resistance, and resistance, how can we get the units of specific resistance? Rho equal to, we know the units of resistance, that is ohm. Units of resistance is ohm, and A is cross sectional area. If you write cross sectional area in CGS units, centimeter square, and length in CGS units for example, if you take meters, for example, if you take SI units, meter square by length in meters. Okay. So, length in meters. So, resistance units is ohm meter. Specific resistance units are ohm meter, right. Ohm meter. Now and the resistance units, we know that resistance units are ohm. Okay. And one more thing is that reciprocal of, we know that reciprocal of resistance, we know that resistance is equal to rho into L by A. Okay. Already we know that conductivity cell measures resistance, and frankly speaking, conductivity cell measures the conductance of the solution. Conductivity cell measures the conductivity of the solution. So, how? Because reciprocal of resistance is called conductance. Reciprocal of resistance is called conductance. For example, if you take reciprocal of this value 1 by R into 1 by rho into 1 by L by A. Okay. So, reciprocal of resistance is called conductance. Reciprocal of resistance is called conductance, and this is called specific resistance. This is called specific resistance, and reciprocal of specific resistance is called specific conductance, that is being represented by kappa, right, and into 1 by L by A. So, specific conductance, we can write specific conductance kappa is equal to C conductance into L by A, conductance into L by A. So, we know that kappa units for kappa are C. C is conductance. Conductance units are reciprocal of resistance. What are the units for resistance? O. So, units are ohm, conductance units are ohm inverse, and length units are centimeter, and cross sectional units are centimeter square. And now we have taken CGS units, right. So, ohm inverse centimeter inverse, ohm inverse centimeter inverse. If you take SI units, then it is called ohm inverse meter inverse. So, these are the units for specific conductance. These are the units for specific conductance. Okay. So, what are the units for conductance? Conductance units are ohm inverse, and specific conductance units are ohm inverse and centimeter inverse. Okay. And right. So, specific conductance is kappa is equal to conductance into L by A, conductance into L by A. So, where C units are ohm inverse, okay, and length units are centimeter and centimeter square. So, ohm inverse centimeter inverse are the units for specific conductance, right. Specific conductance, and we can write ohm inverse. We can write ohm inverse. Ohm inverse means we can write ohm inverse as we can write it as ohm inverse. You invert this ohm inverse, that is you invert the OHM. You invert this letters MHO, mo, and it is equal to ohm inverse is equal to mo, and nowadays these mo's are represented by Siemens. It is called Siemens. Okay. So, specific resistance units are conductance units are ohm inverse or mo or Siemens. So, specific conductance units are mo inverse centimeter, and this value L by A is called cell constant, conductivity cell constant. That L by A value is L by A is called cell constant, that is called cell constant, right. Its units are inverse centimeter, because centimeter and centimeter square we can get the units of inverse centimeter. So, cell constant units are inverse centimeter, units are inverse centimeters, right. And specific conductance, and now we shall go through the effect of dilution on conductance. Okay, already we are dealing with electrolytic conductors. Already we are dealing with electrolytic conductors. Electrolytic conductors are aqueous solutions of salts, acids or bases. Okay, if you take electrolytic solution, if we add water, that is on dilution, usually electrolytes, the degree of dissociation of electrolytes increases. On dilution, degree of dissociation. Okay, these are the very important points. On dilution, degree of dissociation of electrolytes increases, thereby number of ions increases, thereby their conducting power increases. Therefore, on dilution, conductance increases. Conductance means conducting power of all the ions. Conductance means conducting power of all the ions. So, on dilution, degree of dissociation of electrolytes increases. As degree of ionization increases, number of ions increased. So, the current carried by ions also increased. So, on dilution, conductance increases. On dilution, conductance increases. Okay, you should keep this point in your mind. On dilution, conductance increases. Conductance increases. So, but what about specific conductance? Already we derived the equation for specific conductance. Specific conductance kappa is equal to conductance. Specific conductance is equal to conductance into L by A, that is cell constant. If you take if L equal to 1 and A equal to 1, what happens? Kappa is equal to conductance, that is specific conductance is equal to conductance. Specific conductance is equal to conductance. So, specific conductance is the conductance of solution enclosed. Specific conductance is the conductance of solution, solution enclosed between two parallel electrodes separated by a unit length and unit cross sectional area, right? Okay, so specific conductance is the conductance of solution enclosed. Okay, I repeat, specific conductance is the conductance of solution enclosed between two parallel electrodes separated by unit distance and unit cross sectional area of this conductivity cell, right? So, specific conductance is nothing but unit. If you take a unit length is 1 centimeter and if you take unit cross sectional area is centimeter square, then volume of the solution is 1 centimeter cube. That is, specific conductance is conductance of 1 centimeter cube solution, right? Specific conductance is conductance of 1 centimeter cube solution. 1 centimeter cube means 1 ml solution. So, if you take SI units, SI units, that is 1 meter and 1 meter square, then specific conductance is conductance of 1 meter cube solution. 1 meter cube is equal to 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 1000 liters. 1000 liters. We can write 1000 liters. We can write decimeter cube. Liters we can write liter is equal to decimeter cube. So 1000 into deci means 1 by 10. 1 by 10 meter cube. 1 by 10 meter cube. So 1000 by 10 cube means 1000 this cube, that is 1 meter cube. 1 meter cube is equal to 1000 liters, right? So, specific conductance is the conductance of 1 centimeter cube solution or 1 meter cube solution. Usually we say the definition, specific conductance is the conductance of 1 centimeter cube solution enclosed between two parallel electrodes separated by 1 centimeter distance and 1 centimeter square cross sectional area. And we can define another definition for specific conductance. Specific conductance, if L equal to 1 and A equal to 1, then it becomes K equal to C. That is, specific conductance is conductance of solution enclosed between two parallel plates, two parallel electrodes separated by unit distance and unit cross sectional area, right? So already we learned that we know that on dilution conductance of a electrolyte solution increases, but what happens in case of specific conductance? On dilution conductance increases, on dilution conductance increases, okay, but on dilution specific conductance decreases, specific conductance decreases. Why? Because specific conductance is conductance of 1 centimeter cube of solution. So with increasing the dilution, that is, we are increasing the volume of the solution, so the number of ions present in 1 centimeter cube of solution decreases. 1 centimeter cube means 1 ml. So when we are increasing the dilution, the number of ions in 1 centimeter cube or 1 ml solution decreases. So their conducting power decreases. Specific conductance is conducting power of 1 centimeter cube of solution of electrolyte. But on dilution, when we dilute the solution, the number of ions present in 1 centimeter cube of solution decreases. That is why specific conductance decreases. Specific conductance decreases. Now we shall go for electrolytic equivalent conductance and molar conductance, right? Now equivalent conductance. Equivalent conductance, that is represented by lambda C. Lambda C. Equivalent conductance and specific conductance are in relation by the equation lambda C is equal to specific conductance kappa into 1000 by normality. 1000 by normality. This is the relation between equivalent conductance and specific conductance. Okay, so let us derive the units for equivalent conductance. Kappa is C into L by A. We no need to consider the numerical value when we are deriving units. Normality, gram equivalents. Normality means gram equivalents of solute, number of gram equivalents of solute present in 1 liter solution, 1 liter what, right? So C into L by A into liter by gram equivalent. Okay, so units for conductance is ohm inverse, and units for length is centimeter, and units for square cross section area is centimeter square. Liter is 1 liter is equal to 1000 centimeter cube. Okay, gram equivalent inverse, gram equivalent inverse. So centimeter cube into centimeter, centimeter power 4, centimeter square cancelled. So ohm inverse, ohm inverse, ohm inverse centimeter square gram equivalent inverse. So units for equivalent conductance are ohm inverse centimeter square into gram equivalent inverse, right? So equivalent conductance is the conductance of a volume of solution containing 1 gram equivalent of electrolyte present or enclosed between two parallel electrodes separated by a unit distance and unit cross sectional area, right? So as in the case of so equivalent conductance is the conductance of volume of solution containing 1 gram equivalent of electrolyte enclosed between two parallel electrodes separated by a unit distance, right? And molar conductance and molar conductance. Molar conductance and specific conductance are in relation by equation kappa into 1000 by molarity, molarity. So we can write kappa when we are deriving units, no need to consider the numerical value C into L by A by molarity moles per liter, moles per liter. So, C into L by A into liter by mole. Okay, units for liter of conductance is ohm inverse. These are the length unit centimeter, cross section area centimeter square. 1 liter is equal to 1000 centimeter cube, right, and mole, right. So, ohm inverse centimeter square mole inverse are the units for molar conductance, right. So, in this way specific conductance is in relation with the equivalent conductance and molar conductance. So, these are the some terminology of electrochemistry. In the next class I shall come up with what are the required concepts to understand the electrochemistry concepts. Thank you for watching.